In this video, we're going to start talking about how to solve different equations graphically. And in particular, we're going to focus on rational equations and how we can use the GeoGebra to help us solve more complicated problems that would be very involving to do by hand. So first, if we want to solve problems in part A over here, and in general, anytime we want to solve rational equations, as we say in the instruction, we want to set each side to be its own function or equation and graph these two sides separately, and then use a graph to determine where the solution is to the equation. And for example, here, if we have the problem in part A, we can let our f of x be equal to x over x plus 3, and we can call the other side be g of x, and g of x would be equal to 4. And that's what we want to put into GeoGebra or any graphing facility in general. And once we have these two graphed overall, and remember, anytime we want to solve equations graphically, what we're really looking for is where they would have the same x value and same function output. That's essentially what it means to have the two parts to be equal to each other. So once we define f of x and g of x, to solve this equation, we're looking for what x value will these two function output be equal to each other. And it might be multiple values depending on the content. And in this case, we would say for what x values would f of x equal to g of x. In other words, once we graph it, we want to find where the y values would be the same and also x values would be the same. Graphically, that means we would be finding one point where these two graphs would intersect with each other, and that's what we're going to be looking for. So going to GeoGebra, the first function we have is x over x plus 3. So I'm going to go ahead and put that into the input, and we have x over x plus 3. Make sure you put x plus 3 in the parentheses in this denominator over here, and that's what the graph would look like once we graph it. And then we also have g of x equal to the constant 4, so we can go ahead and graph that as well. And once we graph them, we can see right away in the window that we have this intersection of the two curves in this case. And as we said, in order to solve the equation, that's exactly what we're looking for. So to get it, we can use the intersect option. Yours the default should just say a point, and in order to find the intersect, we want to click on this lower right corner triangle and choose the intersect option. That way you can find, using GeoGebra, the intersection of these two curves over here. So just select the blue curve and the red line consecutively over here. I think I misaligned a little bit, so it says undefined, but make sure you click on this line over here. There, I think now I actually got the line over here. And once you do so, you can actually see that we found the point is negative 4, 4 over here. And you can actually see C is exactly at the intersection of the two curves. So just be careful when you select the curves, make sure you're actually selecting the two curves over here. And as you select the curves, there should be highlighted on the left column over here, and we found the solution is negative 4, 4 in this case. So this problem, you can see we could have done the problem with just solving everything by hand, but just by looking at the graph, it gives us an idea. If we have more involved equations, we can always fall back to graphing and use it to solve even more involved problems if we have questions that are a lot more complicated to work with in this case. And here we say we found the intersect is going to be negative 4, 4, and to answer the question, we should say the solution is x equals 4, because when we're solving an equation, we're solving for x over here. So I'd say the solution is, you can use the set notation. And if you are wanting to check your solutions overall, you can always plug in -4 into the original equation and check whether that is a correct solution overall. And in this case, if you want to check your solution, what you want to do is we can go ahead and do it down below. We can go ahead and plug the x value, -4, into our expression. So anytime you see x, plug -4 in, and we would have -4 plus 3 in the denominator, and we want to check whether this is indeed equal to 4, and here we get -4 over -1 is equal to 4 over here. And we can see 4 is indeed equal to 4, so we can be sure that our solution is correct. And in this case, we can easily check the solution because we have pretty nice and even numbers, and in particular it's an exact value. But occasionally you might see questions where your solution is an indeterminate decimal. That means you have to round and things like that. You can still do checking process in that case, you just have to work with rounded values a little bit, but still the idea is the same, that you can go through the checking process by hand as well once you have a solution, because once you have the proposed solution, it's a lot easier to check rather than trying to find this one single value that would work in a more involved equation. Now moving on to part B, we can do the same strategy as before. We can let our f of x be equal to x over 5x minus 30 minus 2 over x minus 6. So you can see when we're working with this type of method, we're not very particular about what type of format we need to start with. We can start working with any form of the rational equation to start with. And on the right hand side, we still have a constant, g of x equal to 1 over here. So I'm going to use GeoGebra to plug this in, and I'm just going to have to take a peek at the equation. And I'm going to delete everything we used earlier so that we can focus on the new graph. Here f of x is equal to x over 5x minus 30 and subtracted by 2 over x minus 6. And once we do so, we can see this purple curve is going to be the graph. In g of x, this is going to be the line, horizontal line again, because it's a constant function. So we have g of x is equal to 1 over here. Feel free to zoom in a little bit as well, and just to focus on this point. And then to find the intersect, we can do the same thing. We want to focus on the line, make sure the line is highlighted over here on the left. You can see once you click it, it's highlighted, and then we want to hit the curve over here. And then you will see A is plotted over here at the intersection of the two curves, and we get that the intersection is at 5, 1. So we get intersection at 5, 1, but to answer the question, we can say the solution is 5 over here. And when we're solving, it's implied that we're solving for x, because x is a variable in the original problem over here. Again, you can check and see whether this is proper over here. And once we plug 5 in, we will get 5 over 5 times 5 minus 30 minus 2 over 5 minus 6. And we want to check whether that's equal to 1 on the right hand side. So on the left we have 5 over 25 minus 30, which is -5, and minus 2 over -1. And we want to check whether that's equal to 1. So 5 over -5 is -1. Minus 2 over -1, which becomes plus 2 over here. And we want to check whether that's equal to 1. And we do have 1 equal to 1. So yeah, indeed, we can confirm that the solution is equal to 5 over here. And when you did everything correctly in the graphing facility, you shouldn't have to check, or your check should always work out over here. But I'm just here to demonstrate that you can always check your process just in case that you didn't quite click on the curve like I initially did. But in general, Decimals or GeoGebra should show that you have found the correct point by plotting where the intersection is. Now moving on to part C. In part C, we have these two sites. We can define f of x to be equal to negative 7r plus 4 over r minus 4, and g of x equal to negative 7r over r minus 8. So going into GeoGebra, we can do the same thing. I'm going to go ahead and delete the other points. So the input, the first one, f of x, is equal to, make sure to put parentheses, negative 7r plus 4 all over r minus 4. Yes, because the question was for r, I should have done f of r. That's what GeoGebra is showing. So it will be g of r in this case, which I didn't pay attention to. So our variable should really be r, and then it'll be graphed over here. Anytime you want to zoom out, you can scroll down to zoom out over here. So make sure your variables are consistent, otherwise GeoGebra won't recognize it. And then we have g of r. That's equal to negative 7r divided by r minus 8. Alright, so we have this graph with red and green curves over here. So if we want to look at the intersection over here, first thing I want you to notice that we have clearly an intersection over here, but we also want to zoom out to be a little bit more careful to check whether there's any other intersection in this case. So we see that there's an intersection in this, and I'm going to go ahead and use a tool to find the intersection again, and we found the point of intersection will be 1, 1 over here. And GeoGebra should generally show any points that are not, even if it's not visible in the screen. And here we have the point 1, 1 be in the intersection. So we can say the solution is 1 over here. The solution set is 1 in this case. And we can check our result. And that gives us negative 7 times 1 plus 4 all over 1 minus 4. We want to check whether that's equal to negative 7 times 1 all over 1 minus 8. So on the left hand side, on top we have negative 7 plus 4, which is negative 3. On the bottom we also have negative 3. On the right hand side we had negative 7 over negative 7. So if you simplify it, you will see 1 is equal to 1. So we do see the solution is indeed 1 over here. And lastly, we have a question in part D. We can do the same strategy as before. F of x equal to this expression on the left, and g of x equal to negative 9 over x squared plus 15x plus 54 over here. And once you plot this in GeoGebra, I'm going to have to take a peek over here. So f of x equal to 8 over x plus 6 minus 9 over x plus 9 over here. So now I can move it back. That's what the function should look like on the left-hand side, because it's a sum of two rational expressions. It ends up being looking like this, and that's the first one we want to graph. And the second one, g of x, is equal to -9 over this quadratic expression. Alright, so we have the blue curve like this. So they are essentially the same shape, but in opposite direction in this case. And now we can go ahead and find the intersect of the two curves. I would be careful in selecting the two curves over here. And I think I didn't quite get the blue curve. So we have the blue one, and then I want to get the red one over here. Oh yeah. And in this case, we actually found c is equal to 27 comma negative 0.01. So that would be the intersection we want to record. Therefore, we can use this information to find the solution is the set of 27 over here. And now if we want to check over here, again, anytime it's hard to choose a curve, I like to check the solution just to make sure it is proper. And here we have 27 to plug into x. So we have 8 over 27 plus 6. And I'm going to go ahead and plug x in through everything. And in general, we're expecting the number to be messy in this one just because if you look at the y-coordinate of the intersection, it's negative 0.01. That means when I plug the input into each side, I'm expected to get negative 0.01, which I suspect might be a rounded value. And in case you didn't notice when we were checking our solution, for example, in the part C over here, we found this intersection is at 1, 1. So when we plug 1 in, we should get 1 on both sides of the equation in the checking process over here. And similarly, if we look at part A, we had the intersection negative 4, 4. So that means when I plug x equals negative 4, I should get y equal to 4 or output equal to 4 on both sides, and that's what we see in every group. So in this case, I'm expecting the output to be negative 0.01 on both sides. And for this one, I expect you to generally use a calculator to do this process, because pretty quickly you will notice if we simplify it, we have 8 over 33, which 8 is not divisible by 33 to be a terminating decimal. And 9 over 27 plus 9 is working out nicely, but still you will have somewhat messy numbers. Feel free to use a calculator to do this process over here, especially once you move on to the right hand side. You will see the numbers are messy in this case. And in this process, once you check everything, you will get the result. On the left, it's equal to about negative 0.0076, and that's why when they rounded, it rounded up being negative 0.01 over here. On the right hand side, I'm just going to write out one more step over here. This we would have 9 over this huge number, which is 27 squared, plus 15 times 27, plus 54. Which I got 1,188, and if you use your calculator to do this, you will get again negative 0.007575, so as I rounded it to 76 over here. So we do see that they're equal to each other, and they're both about equal or approximately equal to negative 0.01. Because they only saved 2 decimal places in GeoGebra, and that's where you would get negative 0.01 on both sides. And that's how we know the solution is correct. Even though we have some messy numbers in the checking process, it doesn't affect our ability to solve this equation.